I want to take a moment with you guys to kind of, again, do a quick sidebar. It's a workflow process that's going to help you out a lot. I'm introducing how you can work in multiple files at once, right? Because so far we've only worked on one file and it's been all well and good, mostly. But what we have to do now is kind of reference back to what we explored before. Okay, so I'm going to show you what happens when I take the patternized definition that I developed and I flip it up into a vertical plane. And then we're going to start to do it in a warped surface later on. But anyway, so I need to go grab that information from a file and bring it into this file. So let me first save my document because I haven't saved it yet. Week 1, day 3. I'll call it 3D pattern exercise. All right, and then all you have to do is just open up another file. So I'm going to go to File, Open, and I'm going to open I don't remember how much I had in the pattern logic and element isolation. I'm going to open the challenge 1 solution. Do you guys still have that file? If you don't have it, you can get it from the definitions folder here. So it's under our folder, K Gremling, 16, Summer, Arc 222, and then definitions. So this is what it created. Basically, it's just a polygon system. And what I have to do is bring this information into the other project. So it's incredibly simple. You guys are going to love this, I think. If you look up in the top right corner, there's the name of the file that you're working on, right? It's written at the top in the actual application title, but then up here there's this little blue button. If you click that, you'll see that the file we were just working on and this file are shown here in a list format. That's important because you can now basically flip back and forth between multiple files while you're in the Grasshopper user interface. So all I have to do now is select this whole thing and Control-C to copy it, and then go to your new file and then Control-V, and it'll be pasted in. Just make sure you don't deselect it before you move it off the other stuff that you created. So I'll slide it down. Is that making some sense to you all? Do I need to give you a moment to get caught up?
How to open the challenge 1 solution?
I'll come around and help everyone out on that. All right, so before I start applying it to a kind of warped surface like this one, I'm going to go through the process of just making it vertical first, so that you can see what the difficulties are going to be. So essentially, what I want to do here is I could either just create a new surface, or I could go to the beginning of the square grid and change the axis that it's working in. So I think first I'm going to do that, although yeah, the base planes might map the whole way. I think the base planes might actually borrow the properties. So let's try it and see if it behaves, and then if it doesn't behave, I'll show you a different way of making it not behave. So anyway, if we reorient the grid, right, we can do that by establishing a new plane for it to operate in. So and that's what this function is here. We haven't really used this much except for overriding the plane of the geometry with a point. But in this case, I'm just going to reorient the whole thing by going up to Vector and Plane. And just like your unit Z, unit X, unit Y, for vectors, you can just basically take your predefined world planes here and reorient it. So I'm just going to choose the YZ plane, and I'm going to plug that in to P. Aha, it did do what I wanted it to do. So notice that the geometry is still in the XY orientation. That's an important little conundrum that we've just discovered, right? How do we get the geometry to then match if it's not in the XY plane? It's very, very significant. It doesn't really, I'm not going to show you all the different formats of how this happens, but I will say this, we're going to have to then use what's called a surface normal in order to orient it. But on a similar note, what I'm first going to do is sort of retrofit this definition to apply to the center point of every single one of these panels. And there are going to be some difficulties with that. So what difficulties do you think we might encounter? Just anything you think might go wrong.
Overlapping.
Overlapping how?
We already wrote it as overlapping.
Right. That's a very good point, because what you mentioned is that the panels are no longer all the same size. So how do we measure that overlapping rule? And the truth is, it's actually incredibly difficult. There are ways of doing it, but it's kind of a nightmare. So usually what you wind up doing is doing it manually. So yeah, that's one of the major issues. The other one is obviously the one that I just introduced to you, right? And that's the direction of the actual curve that we generated, or polygon. So we have to do a little bit of a thing first. I noticed that I don't really need this other surface right now, so let's get rid of that one. It was really just there for me to show you the difference between the two, so go ahead and delete that. And we're going to operate off of this surface right here, or this deconstruction right here. And what I'm going to do is just basically take bits and pieces of this and start moving it up and connecting it as I see fit when I need it. Okay, so I said that I want the polygons to be mapped to the center point of every single one of these panels. Okay, so do any of you remember yet how you find the center point of a panel? I think I only showed it to you once or twice, so it's okay if you don't remember yet. What's that? Yeah, area. All right. You guys are quick. All right. So under surface and analysis, it's this one right here called area. It's totally non-intuitive. It's really not something that just, you would think the centroid lives in. So anyway, the centroid is a product of measuring the area. So when we plug the faces in, we can get the center points of all the panels. And then if we were to, for instance, well, let me think through the smarter way to present this. Yeah. All right, so I think what I would prefer to do is probably just start constructing it backwards again. Since the square grid is going to go away, that means that the plane is going to go away, and then it's really just a polygon anyway. And then that's going to go away as well. So we could pretty much just kind of reconstruct it. So what I'm going to do here, is go up to curve and primitive, and I want to, oh, you know what? Hang on. There was a quick shortcut that I discovered recently, and I forget what it is. Oh well. I might want to look into that. Anyway, so what I'm going to do is kind of just get this thing started. I'm going to go to curve and primitive, and I'm going to use a polygon. So the polygon has a plane, it has a radius, and it has segments. Okay, that's very, very important to understand what the plane, radius, or what the plane's role is here. So the plane I mentioned in our patterning exercise, it can be overridden with a point, right? So you all know that. You know that you can just basically map any geometry to a point or a plane. But the other thing that a plane is really powerful for is orientation, because a plane has how many axes? How many axes are present in a plane? Two technically, but really there are three, right? Your x, your y, and your z. So ultimately, the z-axis is considered a surface normal. So let me show you, and I just like to go to Google because it's got a ton of diagrams that just shows you what a surface normal looks like. Surface normal. This is my favorite diagram. So a surface normal is basically, sorry, I'm tired. The surface normal is basically the perpendicular angle from the surface at any point on the surface. And it's perpendicular to the tangent. That's important to understand. So the tangent, I'm getting kind of packed on the board here. If you warp a surface like this, right, your center point goes out here and your tangent is exactly 90 degrees from your radius. That's your tangent. Now your normal is exactly 90 degrees from that tangent plane, or whatever point on the surface you are. Does that make sense? So it's basically the continuation of the radius along the surface, if there is a radius. But it gets really complex when you have a warped surface like this, because they all kind of splay out in different directions. So it's just kind of something to be aware of, that it's going to get really crazy. Sometimes they're kind of leaning in on each other, other times they'll be, you know, leaning outward. So for the polygon, the plane is the operation we're going to need. So let me kind of get us going for the actual plane designation. This part is really complicated and it's not intuitive. So pay close attention to this one, because we're going to use it a lot. Okay, we're going to use it a whole lot. So under surface and analysis, there is a pair of tools that we need, and it's called the evaluate surface and the surface closest point. So drop both of those in. Under surface analysis, use surface closest point, and then also bring in evaluate surface. So take a look at the input values of these. You need to provide both of them with a base surface. So base surface, base surface. So that's pretty easy. We know that it's going to be the faces right here. Then you realize that on the other one, you're going to need your sample points. So these are the points on the surface from which you're going to find the normal. And so that would essentially be the centroids that we've just created, and that's those right there. So now, because the evaluate surface is incomplete, it's asking for the UV coordinates to evaluate. And so if we take our surface closest point, which gives us UV points. Those are our UV coordinates that we're going to test. And so the UVP gets plugged into UV. So I'm just going to group both of these together and label them under surface analysis, because they pretty much go hand in hand almost all the time. So now let's look at our surface. When I select Evaluate Surface, you can see that a series of planes have been mapped across this surface. And so at this point, it's super mega ultra easy for us to just take the, in this case it's called a frame, right? Because we have the center point, which does not have an orientation. We have the surface normal, which is an axial relationship. And then we have the surface frame, which is a 3-axis relationship. Okay, so that's important to know too. So the surface frame we plug into P. And then when you select that geometry, you can see them being mapped across the surface. All right.
Can you zoom out on the grasshopper?
Yep. So I guess I didn't really need to copy all that in. But it's good that you know you can copy things in. So. Okay, so I'm going to stop this video here, do some troubleshooting with you all, make sure you all have what you need before we move on to a couple more things.